Hello students, in the previous lectures I told you that why do we find the limit of a function at a point? What what is the necessity to find the limit of function at a point? Now in this lecture we'll discuss when will the limit of function exist, and if the limit exists, that is unique, and how do we show that if the limit of function does not exist with the help of Cauchy criteria. So now the first thing for that is prove that limit x touches to a f of x exists if and only if limit x is to a from negative of fx and limit x is to a from positive fx both exist and are equal. That is, limit of function at a point will exist if and only if uh, left limit of function at that point exists, as well as right limit at that point exists, and both the limits are equal. So now we'll prove the necessary part of this theorem. Necessary part means we'll assume that limit of function at a point exists. Then we'll show that left limit of function at that point exists, as well as right limit of function at that point exists, and both the limits are equal. So we are proving the necessary part. Necessary part, we write in this necessary part, or this is necessary part, or if part. So we have assumed to prove the necessary part, let limit of the function as x reaches to a of fx exists and equal to L, say we have suppose that it's equal to L. So this means therefore limit x is to a of fx is to L. Now the definition of limits, if fx approaches to L as x approaches to a, then the definition limit we have a given epsilon greater than 0. This given means for every problem and every term we decide the value of epsilon, however small as we can. There exists a real number delta depending upon epsilon greater than 0 such that fx minus L modulus is less than epsilon for all 0 is less than modulus x minus is less than L. So this is the definition of limit. If this holds true, if limit x is to a of fx is equal to L holds true, now this is the mathematical form of this result. So we use this form in solving the things or in improving the. Now this thing is holds true for this. Now we convert this domain. This domain we can write this neighborhood of point A, this is deleted neighborhood of point A, deleted symmetric neighborhood of point A. This will be written in S form. Means this is neighborhood. If I draw the graph of this here, this is delta, this is delta, this is A point, this is 0, this is A, this is 0, this is A minus delta to A, and A to A plus delta. This is this to this, and this to this. So meaning of this is we are discussing, we can take the value for all value x from here or here except one. Your fx minus L will lie with fx minus L model this is less than epsilon means to draw the graph, L will be here. If you take the value of x from here, L is here, this is L plus epsilon, and this is L minus epsilon. Value of this will lie between fx will lie between this and this. Now, or we can add now if this result is they are all real numbers. Take the x value from here, this is less than epsilon. So when x belongs to this is less than epsilon. When x from this, so we separated them. We written it. So when this equality holds true for x belonging to this, union this means we have separated them. Therefore, this holds true. Fx minus L less than epsilon for all 0 for all x belonging to e minus delta 2, x from e minus delta 2, e minus delta 2, e minus delta 2, a and fx minus L less than epsilon for less than epsilon for all x belonging from a to a plus delta. Now, reverse interpretation of this, given epsilon greater than 0, definition. We are interpreting definition limit in a reverse order. If given epsilon greater than 0, however small, there is possibility of delta such that fx minus L is less than epsilon for all x belonging from e minus delta to a, and given epsilon greater than 0, however small, there is positive limit delta such that fx minus L modulus is less than epsilon for all x belonging from a to plus delta. So this is definition of left limit of function x is to a of fx, and this one definition of the right limit of the function at x equal to a. So on there is a difference of domain to this domain. Domain implies left limit. If the limit of function at a point exists, then left limit at the point exists. If the left limit of function at a point exists and equal to L, then left limit at that in the neighborhood of at that point will be equal to L, and right limit will be also equal to L. So, left hand limit and right limit both exist and at a and are equal to left hand limit and right hand limit both exist at a and are equal to, right? Means if the limit of function at a point exists finitely, means the left limit at the point exists, and that will have the same value, and right limit at the point will have the same value. Now sufficient condition. We'll suppose that sufficient condition means this is a necessary sufficient condition, sufficient reverse order, or only if condition. Let in the sufficient part we suppose that limit x is to a from negative fx and limit x is to a from positive fx both exist at a and equal to L say. Suppose that left limit and right limit of the function f in the left neighborhood and right neighborhood both exist and equal to L. So this both is equal to L. Now, if they are equal to L, now definition of left limit. Definition of left limit, right limit. What to prove? If left limit at a point exists, right limit exists, what to prove? We'll prove that limit of function as it is to a exists and also equal to the same value. Now, what does this imply? We suppose this is true and this is true. Limit x is to a from negative, or as x is to a from negative, fx approaches to L. Definition. This is definition of left limit. What will definition? What this will implies? This will imply given epsilon greater than 0, however small, there is a positive number delta 1 depending on epsilon greater than 0 such that fx minus L is less than epsilon for all epsilon from. Now this is left limit. And again, fx approaches L as x approaches a from positive. What does this imply? This implies we are given a epsilon, same epsilon. Value of epsilon will be decided only once in every problem or any theory. Epsilon greater than 0, how small? There is a positive number delta 2 depending on epsilon such that fx minus L is less than epsilon for all x belong from right neighborhood. Now this is left neighborhood. Now in order to combine the result of suppose now delta, if I suppose that delta is number, if delta 1 is in this case delta 1 delta first equation first, this is first and this is second. Now delta If I suppose delta 2 to be greater than delta 1, delta 2 be greater than delta 1, so the left neighborhood will be left neighborhood, this neighborhood will be this neighborhood, delta 2 is here, delta 1 is here, so delta 2 is here, delta 2 is here. This is a minus delta 2. Now this neighborhood, if the this first inequality holds true in this interval, second inequality holds true in this interval, then both inequalities will hold true. Both inequalities, if I suppose delta 2 minimum of this, now I am making this domain common, equal domain, this domain I would common. So if I delta is less than this, so delta 2 greater than this, so in this whole domain from this to this, now in this case delta is equal to how much? If it is delta 2 minimum of this, means implies delta is equal to delta 1. Delta 1 means now I am making the common symmetric domain on both sides. So from this to this to this equality, both at this and this holds true in this common domain. This is a common domain for this common domain. So common for the domain. Now combining first and second, this fx minus L less than a minus delta 2a. Similarly, this is less than a 2a plus delta. From this to this, and this to this, I'm making it a symmetrical domain. So when I combine this both two, this inequality holds true for all x from their union. Their union will give us fx minus L is less than epsilon for all 0 less than x minus L is less than delta. Delta implies, now definition again, given x equal to 0, this position delta depends on epsilon such that fx minus L modulus c less than epsilon for all 0 less than x minus e less than delta implies limit x to a of fx exists and is equal to, right? Now we have concluded in this theorem that if at a point left limit exists, right limit exists, and both are equal, then the limit of the function at that point will exist and equal to same. Or if or other way, necessary word, if the limit of the function at a point exists, means left limit at that point exists as well as right limit exists, and all the values of values of left limit, right limit is the same as the values of limit. Now next term is if the limit exists. The next term is will the limit will be unique. So next we'll prove that if the limit exists, that will be unique. If limit x to a of fx exists finitely, then prove that it is unique. Proof. The proof is this theorem is we'll prove this by contradiction. This means we will suppose that the limit of function as x approaches to a of fx's have two different limiting values. So that limit x approaches to a of fx have two limits, say L and L. When I said that there are two limits, this will converge to two different numbers. So we suppose that one will be L and that will be L dash. That is there are two real numbers. Either they are two different limits, different number. L is not equal to L dash. So if there are two numbers, so without any loss of generality means one of them will be greater. Either L is greater than L dash or L dash is greater than L. So without loss of generality means we can assume any one of the two things. We suppose, let us suppose that L dash is greater than L. If L dash is greater than L implies that is L dash means L is greater than 0. So here now we are fixing this given epsilon. We are fixing this given epsilon. So let epsilon is equal to, in every problem, every theorem, we fix the value of epsilon. So in this problem also we fix the value. Let us take epsilon to be L dash minus L by 2, because this is greater than 0, thereby 2 divided by 2 will also greater than 0. This is greater than 0. Now epsilon, given epsilon greater than 0, we have fixed the value of epsilon to be this, and this is possible. Now limit x is to f x is L, x equal to L. Definition of limit. What does this imply? This implies given epsilon greater than 0, however small. So we fix this value. This value, uh, uh, this value depend, because L and X limits, they are fixed numbers. So this will be the minimum value of epsilon. This is a real number. How small? Uh, there exists a positive number delta depending upon epsilon. Positive number delta greater than epsilon, or we can write real number delta delta 1 depending epsilon greater than 0. There one is 0. Yeah, or we can find a positive real number delta 1 depending on epsilon greater than 0, such that fx minus L is less than epsilon for all 0 is less than x minus e less than delta 1. Means for all for a deleted neighborhood of format, deleted delta 1 deleted neighborhood of A. Delta 1 deleted neighborhood of A means delta 1 A minus delta 1 to A minus delta 1 to A union A to A plus delta 1, or A minus delta 1 to A plus delta 1 excluding this is the meaning of this is the meaning of this inequality. Okay? And other limit is because this function have two, we have suppose this function two limits. Other limit is again limit x to a of fx x equals to a x equals to a of fx x equals to a of x to L dash implies definition of limit. What does this imply? This implies given epsilon, same given epsilon will be same. How small? There is positive limit delta 2 depending on epsilon, such that we can find a positive limit delta 2 depending on epsilon, such that modulus of fx minus L dash is epsilon for all less than x minus a less than delta 2. First and now again first equality, this fx minus L is less than epsilon, fx minus L is less than epsilon. For this means if I give a pictorial representation for this domain, this is equal to a minus delta 1 to a minus delta a to a plus delta 1. This is the root, and the second result is true in this interval. Second result is true this from this to this. So both the results, both this fx minus L and fx minus L dash modulus is less than epsilon in this is a common domain for this. Common domain. There is a common domain for this. Common domain. So that's where we have taken. Let's take delta to be, so that both inequalities holds true. Both inequalities holds true. So delta 1. In this case, delta 1 is equal to, again delta 1 is equal to delta is equal to delta 1. So this is a common domain in which both these inequalities, this inequality, and this inequality holds true. Right? It's common domain. So first and second we do this. Now from first to second, this is true. Now that this common domain, in this common domain, both the there. Now we're going to prove this, prove the or contradiction. Let us take L dash minus L, because this is a positive number. So this can be written as modulus L minus L dash. L dash minus L, L dash minus L is L dash is greater than 0 when it's positive number. This is a positive number means, so L dash minus L can be written as L dash minus L modulus. So if L dash minus L is equal to 2, then L dash minus L modulus is again 2. To simulate this in this way, we can write this as L dash minus L. This is the value is same. So this. Now we'll use the third and fourth, because we know the common domain in which both results are true. We converting into the definition. So we added fx, separate fx. If they cancel, this is the same. Now we convert it into this form, this form, or this form. So this is equal to L. We took f minus 1 common. This will become fx minus L. Minus common, equal to minus, plus this minus, the same thing, and this is equal to 0. Now we use the two result. This is A and this is B. Modulus of A plus B less than modulus of A is modulus of B, and modulus of minus X is equal to minus A. Modulus of minus A is equal to modulus of A. The same thing. So this become equal to, now substitute the value from this third and fourth. This and third, this and this are true. So substituting, when will be there less than this? They will be there less than epsilon by 2. Epsilon 2. What the domain for this? Domain for this is for all 0 less than x minus a is less than delta. This is less than 2, common domain. So L minus L dash, L minus L less than 2 epsilon is equal to L minus L dash. This is equal to this. Now when we conclude this, L minus L dash is here, this is less than. We substitute from third and fourth. From this, we have substituted the greater number. This is greater number, less. So L dash minus L dash minus L will become less than L. Now, which is contradiction? Difference of two numbers is the same number, which is not where possible. Suppose this is 3 by L dash is 3, and L is equal to 2. L is equal to 2. 3 minus 2. L is 2. So this is equal to 1. So one can't be less than 1. That's what this is a contradiction. So contradiction implies our supposition wrong. We suppose if the limit of function exists, any function, if the limit of function at any point we suppose to have two values, that is wrong. If the limit of function at a point exists, that will always be unique, right? Now next another form of this definition. If limit another statement of the theorem. If limit x belongs to a of fx L and limit x is to a of fx L dash, then prove that both are equal. Means it is the same thing. If the limit of a function exists, then the limit is unique, right? Now this is this uniqueness theorem on left and right hand limit correlates based on the second theorem. If left limit of function fx exists finitely, then limit will be. If right limit of a function at a point exists finitely, then the is. In the same way, if the limit of function at a point exists, that is unique. In the same way, if the left limit at a point exists, that will be unique. And right limit of function at a point exists, that will be unique. This will be proved only you have to left limit. If you proving so, you have to suppose the two same limits. In place of limit, you have to write left limit here, and domain will be changed from from a minus delta 1 to a. In the case a delta 2 a to a plus delta 2. Again, you have to take the minimum of both and make the common domain where the results are true. Where the both inequalities hold true, this will be we'll convert this from from a minus delta 1 to delta minimum delta 2 equals delta except e is not equal to x is not equal to domain, and same equality for left as right. You can prove from by changing this domain. You can prove both these parts, both this part and this part, and solve also and prove also, right? Now next term is Next theorem is if the limit x equals to f function fx is equal to L, then f is bounded in the deleted neighborhood of A. Deleted neighborhood, whenever you use the deleted neighborhood of A means we are having a neighborhood of A, but we don't consider the point. We are deleting the point. ठीक है, क्या बोलता है? What does he say? He said if the limit of function x is to a fx is equal to L or will exist finitely, then f is bounded in the given. Now given is limit of function fx at a point exists and equal to L. Now what does this imply in the definition theorem? If fx, this implies as x is to a fx is equals to L. This means we are given epsilon. We have a epsilon given epsilon is 0. How small this positive delta dependent epsilon such that fx minus L is less than epsilon for all g less than x minus A less than delta. Now to prove what to prove? You have to prove that fx is bounded in this deleted neighborhood of A. Up now let me define bounded function. A real valued function fx is said to be bounded if let's say if bounded in its domain if there exists a positive number k, however large, such that modulus fx is less than k for all x belongs to the domain. Now, domain can be changed. Then we can have some neighborhood or anything else. Any in domain we are talking. So, convert that to this bounded function. Let f be any real number. Now, this is definition from here to here. Now, I want to show. We know the limit of function exists. Now show. For the convert. Now I'm converting this function to this form. So let k be any. Now I'm deciding the value of epsilon. Let k be any real number greater than modulus of L. Why modulus of L? We'll come to know later on. And epsilon is equal to k minus modulus of L is k minus k is up k minus modulus of L. Now we'll decide the value of we'll take the value of k greater than modulus of L. Right, and so that the epsilon will remain positive. Now I'm using the definition. So what is fx is equal to? Again equal to, we add plus 1 plus L minus L. You cancel them, you get same number. So modulus of a plus b is less than equal to modulus of a plus modulus b. Now modulus of fx from result first, fx plus L is less than epsilon for all x belongs to this. So this is less than epsilon. Equality we control the inequality less than epsilon plus L, and this is equal to substitute value of epsilon k minus L. In which domain? This is true in domain deleted neighborhood of A. Delta deleted neighborhood of A means x belong from A minus delta to A union open interval A to A plus delta, both open intervals. All variables. Now we got, when we cancel them, we got modulus fx is less than k for all x belongs to A minus delta to A union A2 plus delta. Now definition. Now this is a k any real number. K any real number such that modulus x less than this implies modulus fx is less than k for all x belongs to the delta deleted neighborhood of A. Therefore, fx is bounded in the deleted neighborhood of A. Now let us discuss this in section part. Now important results are, if limit x is to A of fx exists finitely, then the function fx is bounded in the deleted neighborhood of A. We took this part. But converse is not true. That is, if a function is bounded in a deleted neighborhood of A, then the limit of a function may or may not exist in the neighborhood of in that neighborhood of in that deleted, right? If the limit of function at a point exists, implies the function is bounded in the deleted neighborhood of A. Boundary means if you take the value from that deleted neighborhood of A, the function will have maximum as a minimum. But it is not necessary that if the function is bounded in a deleted neighborhood of A, the limit may or may not exist in that deleted neighborhood of A. Next is, if fx is not bounded in a deleted neighborhood of A, then limit does not exist, right? If the function is not bounded in a deleted neighborhood of A, then the limit at that point of that function does not exist. These results are also true for one-sided limits, left limit as well as right limit, right? So what's the conclusion for this? Conclusion is, if the limit of function at a point exists, means the limit of function at a point exists means the function is bounded in the deleted neighborhood of that point. But if a function is bounded in a deleted neighborhood of A, then it is not certain that the limit of function at that point will exist. Now that's it. Now problem is the definition of limit, which we have discussed till now, will be silent about finding how can we show that the limit of function does not exist. Silent about the finding the non-existence of the limit. Now, for that, Cauchy criteria for limit of function is Cauchy criteria. Cauchy, wherever or when in mathematics, uh, Cauchy used his thought. Either he took the 2 points or two functions. We discussed the definitions, and with the help of 2 points. So we have studied the Cauchy theorem, mean value theorem. Cauchy theorem is you can say two functions. Now in case of limit, he took the 2 points from two. So definition Cauchy criteria for the limit of function is, let limit exists to a of fx exists finitely. When we do exist finitely, now we will study one definition, and the other we will just note down the change of the definition limit. If given epsilon, how small, same, there is a positive number delta. Now he has not written here the delta depending on epsilon. Delta dependence on epsilon has treated by the Cauchy, such that fx1 minus fx2 modulus is less than epsilon for all 0 less than xi minus 1 minus a is less than delta for I is 1. Now let me make it clear the difference of the domain. Now this is domain. This is the domain, and A is here. If I write this division of A is here, and A minus delta is here. This is A plus delta is here. Now this is the domain. The domain, and x1. If you write x1, if you write x2, so 0 is less than x1 minus a less than delta. If you write 2, 0 less than x1 minus delta, means we have taken, Cauchy has taken 2 points, one from any 2 points, one from here or one from here, and 2 points from this. Both x1 can be taken from here, or both can be taken here, or one from here, or one from here. Even then, the values of the function fx1 minus fx2 is less than 0, then implies this limit of the function exists. This limit of this function exists, and this is finite. Proof is, with this theorem is, we have applied in the statement you have given that limit of this function exists and finite. So let us prove that this is given. Let's show that the limit of function at a exists and equal to say L. because it's finite, so we suppose this number is L is the limit is L. Now definition of limit. If this is equal to, what does imply? This implies we have a given epsilon greater than 0, however small, there exists a positive number delta such that fx minus L less than epsilon by 2 for all x belongs from deleted neighborhood of delta deleted neighborhood of A. Now we've taken 2 points from this. Real numbers x1, x2, because we are discussing real value function, and both belongs to this, so that if both belongs to this, then this in this and this goes to this means whether we write this x1 x2 this or we write this, they are the same thing. Both the same thing means we have taken the point x1 x2 belonging from this interval, except a minus delta to a open interval union a to a plus delta open interval, either both from here, point from here, or from here, one from here, or one from here, or one from here, right? So this is there. Now, if 2 points, now this inequality holds true for all points. So this holds true for x1. Simplest x, write x1, 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 fx minus this is also epsilon by 2 for all 0. Similarly, if I take x2 from here, x2 endpoint from here, this is again true, right? If you take x from here, x2 from here, or from here, this is also true. X1 from here, x2, this holds true. Now third and fourth, and now this y epsilon by 2. In the definition we have written if the limit is equal to L, so this is fx minus L is less than epsilon, y epsilon by 2. Now answer to this question is epsilon is a very small number. How small you can take? If a very small number divided by a finite number, very small number will remain very small. For example, this is equal to, suppose epsilon is equal to 0.000000000001. So if you divide by 2, what will happen to this? Nothing. This is equal to 0.0000000005. One more 0 and 5. This is still small. And you say, this again, if this was small, this is also small. They are very comparable, very small numbers. So we use this. We divide a very small number by a finite number. Very small number will be very small. So use this concept in proving the theorems. So this is number 2. Now, we have taken the left hand side of the Cauchy value, left hand side of this, because it will be this one here, this one. We do this is less than epsilon. That's why we have taken this epsilon. We prove this by this is less than fx1 minus modulus is less than epsilon for all 0 less than xi minus 1 is less than delta. Guys, before that, fx1 minus fx2 modulus is equal to, we have subtracted L, added L, we're converting that into third and fourth. You want to use the third and fourth result. This result and this result, that's why you're converting this. Domain is known to us, domain and the inequalities of real number. So this and this, so you can go to this and this form and this form. Minus 1 common. So this is equal to fx minus L. This is equal to fx minus L. Minus common. Again, modulus A plus modulus B is less than equal to modulus A, modulus B, and modulus minus x is equal to modulus x. Modulus minus x is equal to modulus x. Now, using the third and fourth is equal to, this is less than epsilon 2, this is less than epsilon 2 for all x, 0 less than xi minus 1, x and c less than delta, I want to means 0 less than x minus a is less than delta, 0 is less than x minus a modulus less than delta 2, delta. Using both the results, we got this is equal to fx minus 1 minus fx1 minus fx1 minus fx2. What is this? It is epsilon for all 0 less than xi minus a less than delta, where I is 1 to 3. Now, definition is Cauchy criteria given epsilon greater than 0, this positive number delta such that fx1 minus fx2 fx2 modulus is less than epsilon for all 0 less than xi minus a less than delta I is 1 to 2. This is complete. If limit x to a of fx does not exist, then Cauchy criteria is very helpful in showing the result. Now, if the limit x to a of fx is not equal to L, not a finite number, then by Cauchy criteria, if given epsilon greater than 0, how small, there is positive number delta such that modulus of fx minus L is greater than epsilon. You can search, you can find an epsilon such that fx1 minus fx2 modulus become greater than this some certain finite number for all x belong to this, for all x belonging to the deleted delta neighborhood of deleted, deleted delta neighborhood of it, deleted delta neighborhood of a, then uh, then the limit of function does not exist. So this helps us in finding if the limit does not exist.